Hi, I'm Ben-Yaakov. This presentation is entitled Silicon Carbide MOSFET Datasheet and Comparison to Igbt, Part 1. Now, the objective of this presentation is to describe the special characteristic of silicon carbide MOSFET and to compare them to the competitor, you might say, which is the Igbt. Please note that there are two videos in my YouTube channel, MOSFET datasheet, which describe the very basic structure of a datasheet, the parameters of a MOSFET, and many other issues related to the characteristic of MOSFET. So I'm not going to repeat this here. So if you are unfamiliar with some of the parameters, please watch these videos which give a detailed explanation of most of the parameters of the MOSFET. Now, the main differences between the silicon carbide MOSFET and Igbt can be summarized here. These are just the highlighted and the very basic differences. Number one, the Igbt is a junction device. There is a junction, therefore there is a stored charge in the junction, and therefore when the device is turned off, there is a tail. That is, the current is not going down immediately. It is sort of dissipating out. So there is a period that there is a still current and there is a voltage on the device. So therefore the losses will be higher due to this tail effect. Now, another feature is that when conducting, the Igbt behaves like a constant voltage rather than a resistance. That is, the voltage on it is about fixed, sort of little dependent on the current, and there's a certain slope, but it's basically a constant voltage, which is around 2 volts. It's a saturation voltage. And of course, today at least, the Igbt is of a lower cost than the silicon carbide, which is higher cost, primarily also due to the material itself. The silicon carbide material is more expensive. Now, as for the silicon carbide, it is a fat device. There is no junction, so therefore there is no stored charge, and you can switch it very quickly depending on the drive that you have at the gate. And when it is conducting, it's behaved like a resistor. There is the RDS on, and the higher the current, the higher the voltage drop, like a resistance. And of course, I've already said, today at least, it's more expensive than the Igbt when you compare it for the same current. That is, due to the fact that the Igbt has this tail of the current that turn off, the switching frequency that you can get is lower with Igbt. We'll see it later on than with silicon carbide. So comparison is really not that simple. But if you just compare devices of same current capabilities, not considering the switching frequency, then the Igbt is much less expensive. But of course, if you bring in the issue of switching frequency, then it's a different story. So the next thing is I'm going to look at some of the data sheets, and let me start off with the general description of the silicon carbide datasheet. For the silicon carbide, I've chosen this unit here from Cree. It's a silicon carbide power MOSFET. It's a 1200 volt device with a drain current specified 25 degrees to 115 amp. RDS on is 50 milliohm. This is very low. It's a very nice device. So the structure of the datasheet, and I'm just describing it in very general terms, is first of all some general information, some things about the package, internal structure, and then we have, very important, a table of the maximum rating. Now this is not the operating condition, but rather the maximum rating. I'll go over it a little bit later. I'm just talking about the general structure here. And this is these are the parameters or the values of the parameters you should not exceed, otherwise the device may be damaged. Then we have the actual electrical characteristics. Here we have more of the information about the voltages, gate voltages, and then very important, and this is an issue that we are going to dwell into, is the switching energy, that is the losses while you switch the device on and off. This is very important because this will determine how fast can you switch the device. We'll talk about it a little bit later. Then we have more of a speeds like turn on, turn off, and as well as in this case here we have the diode characteristics of the device, like the stored energy, stored charge, maximum current, etc. And then we have the thermal characteristic, in primarily the thermal resistance between junction and case. This is this value here. I'll talk about it later on. And then there are some graphs which are related to the parameters which are in the table, but they are giving more information like over a span of voltages, temperatures, and current. And then at the end we do have some information about the way it was tested. I'll talk about it also. This is sort of a double pulse type of a test. And then the package, the size, and dimensions of all the parts of it. So this is the general structure. So let me start off with the very beginning. Let's talk about the device itself. Now we see here a device which has the MOSFET, the silicon carbide MOSFET, and a diode. This is a body diode. This is part of the structure here. This is not an external diode. In IGBTs, we do not have diodes, and if you have in a package a diode, it's actually an add-on. In the case of this particular device, it is an inherent body diode, as it is called, and the characteristic of this diode are not very good. We'll see it later on. Another point that should be mentioned is that we do have two lines going to the source. This is the source, this is drain, this is the gate, and we have two lines. One is the power line, and then we have a line for the driver. So let me try to explain why do we need this extra line. This is the so-called Kelvin connection. Kelvin connection. Now let me first of all say what is a Kelvin connection, and let me start off with a general description. Now if you have a resistor, for example, say a shunt, which is connected here. These are the terminals of the shunt. Say it's a shunt like this, and you'd like to measure the resistance, okay, or the voltage drop, I should say, on the shunt for determining the current. The current passing here, there is a voltage drop on the device, and you'd like to find out what is this voltage. Now one way to do it will be just to take a wire here and a wire here and measure the voltage. Now if you do that, then you have a problem that there is a voltage drop in this connection here, which you actually see as you measure it this way. So the Kelvin connection means that in order to measure a voltage, say, of a resistor in which you are passing current, okay, you connect two wires here in which there is no current passing through, and then you measure the voltage here. So in this case, if there is a, say, connection here and a connection here, these wires actually reflect the actual voltage on this resistance. So this is the basic idea of the Kelvin collection after Lord Kelvin. And in fact, there is a Kelvin bridge for measuring resistances very accurately by this trick. So how does this relate to our case? So let's see, if you have a transistor, it will have some inductance between the source and the actual terminals and also the wiring. And this is the source. And here we have a driver that we feed the gate. Now, normally, we're going to have the return of this driver connected to the general ground of the system. Now, if you feed in a signal here, come here a signal, then this transistor starts to conduct, and as the current starts to build up, there is a problem because there is this inductance, this stray inductance, and therefore there is a large voltage drop. It will take a while until the voltage, or the current I should say, will build up. Same thing goes at a turn off. In this case, there is a current here, and here you try to turn off the transistor, the current is still flowing here, so there are some spikes involved here. So this is a difficulty, especially at high power. The higher the current, the higher the problem, of course, because all is related to dI to dt, and therefore the higher the current, the faster the current, the more problem you have. So therefore comes this idea of the Kelvin connection. Okay, in this case, here is the transistor, and let me put the stray inductance again. But now we have another line, and now the driver, and this driver now should have, should have two outputs. One is connected directly to here, and one is connected to the gate. These are the outputs, and here is the input. And then there is a ground, and of course there is a ground to the driver. So this is a special driver which has uncommitted output transistors. Say it's a sort of a transistor like this coming out of the driver, not connected to the ground, so that you can connect this uncommitted point to this Kelvin. By this, you overcome the issue of this. Now, obviously, there are still some leakages involved because the inner connection of the die, etc. But of course, the problem is one order of magnitude less than when just connecting this to ground without having the Kelvin connection. So this is the reason for this connection here, which is now fairly common at high power devices. Now, another point that we observe is this notch here. And this notch, of course, is due to the fact we are talking about a 1200 volt device, and you have the crimpage distance here, so as to make sure that there are no problem of sparking between the lines here. So this is the very first part here, is showing the device itself, and then there is some general description that the vendor is giving us as to why you think that this is a very good device. It is not important for our discussion here. So let me go back now to the data sheets itself. Okay, so we have this data sheet, and now we come to the maximum rating. Maximum rating, again, is not the operating point, it is the maximum allowable values of various parameters. For example, the drain to source voltage should not be higher than 1200 volt. The gate should not be outside this range, and then there are some other parameters. There is also a value for the continuous drain current. For 25 degrees it's 115 amp, and for 100 degrees it's 85. Now this is a kind of a funny number because it assumes that the casing is kept at a given temperature. So let's go on now with this data sheets and go now to the actual electrical characteristic. This is the operating condition, and here all these are for 25 degrees unless otherwise, of course, specified. So we have the 1200 volt, we have the threshold voltage. This is when the device starts to conduct. It's not much different from a silicon MOSFET. Then we have the RDS on, typical RDS on between 11 to 22 milliohms, and this will be at 25 degrees, and this number here, 28, is for 175 degrees. So obviously the resistance is going up, RDS on is going up, and this is, of course, on the one hand, not very nice because the dissipation will go up, but on the other hand, it helps if you use a number of units like this in parallel. Because if you have a number of units in parallel, let me take out this tablet here. If you have a number of units in parallel, then of course the one with the lowest RDS on will conduct if these are in parallel and the current is passing through them. Now, so if it will conduct more than the device with the higher RDS on. Now, if it will conduct, then it'll heat up, RDS on will go up, so it'll tend to balance the current between these two. I should say that the increase in RDS on of the silicon carbide is less than for silicon. Silicon is the change is much larger, which makes it better in this respect. It's worse in terms of the dissipation and the power loss, but in terms of current sharing, it's better. So the silicon carbide has a little bit of a problem sharing currents because when you take two units, of course, there is some spread of parameters, and it could be, you see, from this to this. So if you can have a unit like this and have a unit like this, you are in trouble because all of the current will go through this unit, and even if it'll heat up, it may not get up to this value, and then it'll still consume the current. So this is the issue of RDS on. Then let's see the important parameters here is the energies. And this is something that is like a major point here. And here we have the turn on switching energy and turn off switching energy. You see it twice. And one says with silicon diode conducting, and the other one is with body diode forward. Okay, and these are energies during at turn on, at turn off, and the values we are talking about is this is around 1 millijoule, and this is about well, depending on turn on and turn off. And turn off, we see that here it's only 0.6, and here it's much larger. This is with the body diode. The body diode will cause higher dissipation. So what is all this about? What are we talking about here? Okay, so the explanation is actually related to the fact that we are testing these energies in a structure which is very typical of a high power converter, which is a half bridge. Okay, we basically, this is the setup for these tests for the energies. Okay, we have the device under test. This is the device under test, and then we have a similar device here, and then we have a inductor here. Okay, this is a voltage source. The current of this lower device has to be measured, doesn't show here. We measure the current of this device. We measure the voltage on this device. And then during the switching, like during, say, turn off of the current, and of course the voltage will go up. This is the voltage, this is the current, this is the voltage. We look at the product here, which is the energy, the area here of the product, V times I. This is time, and this again, this is voltage and current, and this is the energy. So these are the energies which are specified in the datasheet. So the experiment or the testing goes like this. We turn on first the transistor. This will cause current to pass here. Okay? And after a while, we turn off the transistor, and this current will clamp into this upper transistor. And then we turn on the transistor again. This is why this test is called a double pulse. We turn on the transistor again and turn it off again for the actual test. That is, at the very beginning, we build up a current here, the current of the test. Then we turn off this transistor. Under current, that is, the current is flowing here, and we turn off the transistor. And then we turn on the transistor, and in this case, what happens is that the current before turning on the transistor again is now going this way and going through the diode. So when we turn on the lower transistor, which is under test, we are also subjected to the problem of reverse recovery of this diode. And the information that Cree is giving is for two cases. One, that this diode is the inherent diode, that is the body diode of the transistor. And the other case is when there is an external silicon carbide diode, and they specified which one is it, so that you actually test it with the reverse recovery of the silicon carbide diode. Okay, now silicon carbide diodes are Schottky diodes. Now what is a Schottky diode? Or let me start with the silicon diode. The silicon diode, as we know, is a N and P interface, and then you have here a junction area, and this is a regular silicon diode. Now a Schottky diode is a diode between a semiconductor and a metal. This is a metal. In this case, there is almost no charge stored here in this interface. So these are the Schottky diodes. We have a silicon Schottky diodes, and the silicon carbide diode is also a Schottky diode. So this is, in terms of reverse recovery, a good diode, better than a regular silicon diode, and certainly seems to be better than this body diode. Now, although there is no storage in junction, the silicon diode, silicon carbide diode, has some capacitance when it's conducting, and therefore as you move the current backward, you charge this capacitor, so you do have a reverse current. It's not a stored energy, it's more like a charge of a capacitor. So it's not negligible. You can't say that there is no reverse current, but the reverse current is of sort of a different nature. So let's go back now to the data sheet and have a look at the numbers here. Okay, so now we understand a little bit better what all this thing means. So we have here now turn on switching energy, silicon diode in the forward. This is the upper diode, and it is 1.1 millijoule. Turn off switching energy, obviously in this case there is no diode involved, and although it is saying that the silicon, but the diode is not coming into effect, it's 0.8. On the other hand, if the switching is with the inherent body diode, we see that this number is much larger. Well, it's more than twice, and this number, well, it's about the same. Now these are key parameters for switching frequency. Why is that? Because every time you turn on and off the device, and we are talking about hard switching, soft switching is a different story altogether. So every time you turn the device on and off, you dissipate, or the transistor dissipate, this amount of power. By the way, this also includes the power due to the stored energy at the collector to emitter, between the drain and source of the MOSFET, there is a capacitance, C out SS, and there is an energy stored in it. And so these numbers include the fact that whenever you switch the transistor on, you dump this energy into the transistor. So this is a sort of the total sum. Okay, so why is this so important? Again, every time you turn on or off the transistor, this amount of energy is lost or dissipated into the transistor itself. So if we have the energy is, let's say, let's call it energy, as they do. The energy is, say, whatever, say 3 millijoule per on and off switching. Then if you turn on and off the transistor at a given frequency, then the power dissipated will be this E times the frequency. Now, suppose we'd like to run the device at 100 kilohertz. This is a reasonable frequency we'd like to have today. Then in this case, it'll be 3 times 3, 10 to the minus 3, times 10 to the 5th, So this is 300 watts. Wow, that's a lot. This means that the energy, switching energy, is a real limiter for the switching frequency. And this is the most important parameter that you have to worry about. So in this case, if indeed the energy is of this magnitude, probably you can go to, say, 60 kilohertz, and then this will be 180 watts, which will be okay, perhaps. The way to examine this is to consider the fact that when you have the transistor, here it is, and there is some insulator, and then here is the heatsink. Then there is a thermal resistance between the junction and the output, and so the thermal resistance between junction and case is a crucial number, and we can see in a minute, we'll see what's the value here. And then there's some insulation here in between that thermal pad, and so the total could come up to be around, say, 0.5 degrees centigrade per watt. So for 180 watts, we're talking about 90 degree above ambient. So if the ambient is, say, 50 degree, which is not unreasonable, we are talking about 140 degrees. So this is kind of a limiting factor here, because the maximum junction temperature is 175. However, one has to bear in mind that the operating point at which these were taken, and this would be specified here, you see this is 800 volt, 75 amp, okay? So this is a fairly high current. You probably would not like to run this element or this device at 75 amp. At lower current, of course, these values will be lower. In fact, there is a plot, or supposed to be. Let's have a look if we can find it. Okay, here we have it. This is now the on and off, the energy, turn on and turn off, as a function of the current. We were talking about this point here, okay, this point here. And while, of course, if you work at 40 amp or 30 amp, which would be more visible for this device, then the total will be less than 1. So we are in a better position here. This is now a comparison. This is now as a function of temperature. All these losses are a function of temperature. Unfortunately, they'll go up, the total. And here you see that there are two curves, and this one here, the violet one, is for the case in which they've put a silicon carbide diode in parallel, so it's lower here, okay? So it is lower here than without the silicon carbide diode in parallel. Okay, so we have seen that these are the crucial parameters here, and another important parameter will be the input charge that you have to feed into the device. And let's see if we can find the information here. Obviously it has to be here, and here it is. Total gate charge is 211 nanocoulomb. Now this is important because it tells you how much current do you need for the driver the peak current in order to charge or to transfer this energy to the device, to the gate. Now there's also be a curve here, a plot, here it is, which shows the charge characteristics, and here you see the charge that you have to feed into the gate. As the voltage of the device goes up, will go up to 15 volt. This is the nominal value. So here is the 200 and something nanocoulomb that you have to feed in. Now, if, for example, let's do some simple estimate here. If, for example, you'd like to feed the gate with a signal such that the voltage of the gate will have a rise time of, say, let's say 30 nanoseconds. Okay, that will be fairly fast. Okay, so we need to feed in this charge, which is 200, let's say 200 nanocoulomb, and we do have, so the current that we need if we want to feed this charge within 30 nanoseconds, the current will be Q over this delta T, and this is 200 divided by 30. So this would mean that you need approximately 6 amp drive to the gate. So this tells you about the requirements for feeding the gate and turning it on and off. Okay, so let's go back now to the datasheet and see other relevant parameters. Here is the thermal resistance from junction to case. It's 0.27, but again, one has to bear in mind that there is an addition of thermal resistance between the case and the heatsink, because the case itself is the drain, which is high voltage. So when you clamp it to a heatsink, you might have some insulation in between, and the resistance, thermal resistance of the insulation will be at least 0.5 or maybe 0.7. So you end up with something which is that 0.7 to 1 degree centigrade per watt. So this is the limiting factor in terms of temperature rise of the device. Now, as far as the internal diode, there is of course information about the internal diode, and let's see where it is. Body diode, here it is. Here's the body diode characteristic, minus 40, well, let's see, 25 degrees. Okay, so this is the current and voltage of the body diode. Well, they show it in the reverse direction. Now, what we see here is that the voltage drop on the device is fairly high. That is, at 100 amps, say, it's 5 volts, okay? So, among other things, not only that this is a rather slow diode, also the power dissipation of this diode will be high. That is, if you work in a, say, let me go back to the tablet mode. If you say work in a half bridge and say suppose this is a, say, a buck converter, and then current is flowing this way. You turn off this transistor, then the current will flow here, and since it will flow through the diode and the voltage of the diode is, say, 5 volts, the dissipation will be fairly high. So you would have to turn on the transistor in order to reduce the voltage drop. That is, there will be a certain dead time. You cannot avoid it because from the time you turn on off the upper one and you turn on the lower one, you must have some dead time. The diode is conducting, and then you turn on the transistor. Now, the information about the conduction of the transistor in the so-called third quadrant, if this is voltage, this is current, this is the normal, the first quadrant, and here is the third one. This is when the diode or the transistor is in the reverse direction, and this information also should be given as to what is the characteristic of this device when it is in this mode of operation, which is very important, of course, in all PWM converters. So let's have a look at this and see where they got this information. Okay, here it is. This is a 25 degree. This is the third quadrant characteristic at 25 degrees. Obviously, it is the function of the gate, that gate to source voltage, that is, we like to turn the device on. So say when it is 15 volt, well, it is a straight line, and this would mean that it is like an RDS on. So it's RDS on both direction. Let's see what is about the resistance. Say 100 volt, it's about 1.8 volt. 100 amp, it's 1.8 volt. So let me have a look at it. I'm talking about, say, this point here. So this is about 1.8 volt, and this is 100 amp, and the resistance, of course, is V over I, so it's 1.8, 100, so it is about 18 milliohm, which is what we expect from the transistor, from the RDS on in the forward direction. So this is now the issue of the reverse conduction. Now the datasheet, of course, includes information about the rise time and turn on delay, fall time, which are in the nanosecond region. And this is important, but really the final parameter, or the most important one, are the energies involved, okay? So no matter how fast you turn it on and off, this is the value that will affect how fast can you switch the device. Now these speeds, of course, are dependent on the current, peak current that is fed to the gate, and this will be determined by the gate resistance. Here it is 2.5 ohm, but even if you reduce the resistance and the current will go up, this number will not change dramatically. One has to bear in mind that the gate itself and the wires do have some resistance and some inductances, so therefore these are realistic numbers that you have to take into account, and as I've said, the most important part are these energy specified here. So this is, in fact, the highlight, or the most important, I think, parameters of the silicon carbide. And let me now turn to the IGBT. And as a comparison, I have chosen an IGBT. So let me now turn on to the IGBT. Well, here I've chosen an IGBT, but it's sort of comparable to the size of the silicon carbide MOSFET I've shown before. Well, it's not one-to-one. The silicon carbide is heftier, could carry higher current, but the IGBT here is fairly high power. So we are talking about an IGBT that has a current of 50 amp, and this is again a 1200 volt device. And let's have a look at the maximum value, 1200 volt, maximum current of 100 amp, and we have the 50 amp at 135 degrees. That's, well, it's same order of magnitude as the silicon carbide transistor I've shown before. So now the thermal resistance is about the same, not too much different. The same package is the same. By the way, this device has also a Kelvin connection. Here it is. There is a Kelvin connection here. And then let's have a look at the crucial parameters, which are the energy turn on and turn off. By the way, I didn't say that the diode that is shown here is an extra diode that is put into the package. The IGBT does not have a body diode, so this is a fast silicon diode. Okay, so and by the way, the IGBT is not conducting both ways. Now let's have a look now at the energies, which is, as I've said, the bottom line here. Okay, now we see here the turn on energy is 2.3 millijoules, and the total switching energy is 4. It's about a factor of 2 larger than the silicon carbide we have seen before, while the current are a bit lower, because this is for 50 amp, while in the case of the silicon carbide it was for 75 amp. Now we see that the rise time and fall time are pretty much the same, but these are the fall and rise time of the voltage. Now, as I've said, we have here the issue of the tail, and as a result we do have higher losses here. But it is a fairly fast element, and since the total loss here, energy, is about twice that of silicon carbide, or a little bit more depending on the operating point, it would mean that you can run this device at a lower frequency than the silicon carbide. So this actually brings us to the conclusion that the silicon carbide is certainly a much faster device than the IGBT, and that you can run it at higher switching frequencies. But of course there is the cost issue, and if I'll look up now, say looking one of the distributors, we see that the unit price is $12 for a unit. Obviously there's a drop, but let's take as a reference the price of quantity of 1. While if I look now at the silicon carbide, so we are talking here about $92. So it's a factor of 8, about 8, 7 between this and this. So this is the situation we are at today. We have the silicon carbide. It's a nice device, certainly better than the IGBT, no question about that, but still there is this price issue, and then the question is whether in a given application it's worthwhile to use, say, one silicon carbide rather than 2 IGBTs. IGBTs, by the way, can also be put in parallel because the voltage goes up, not in all IGBTs, but in most IGBTs the voltage goes up with temperature. So you can parallel them. And then of course there are ways of interleaving and some other techniques that you can use when you want higher power. So this is actually the end of this presentation. Thank you very much for your attention.